Hello, I am happy to introduce our new work, Unsupervised KB2 text generation with auxiliary triple extraction using dual learning. My name is Hao Fu. This work is done with Beishi, Li Dongbing, and Lam. This is the outline of our talk. We will first introduce the background of our task. Then we will show the detailed structure of our model. Also, I will show some experimental results, and finally, I will summarize the conclusions. Data-to-text generation is a very popular task. It aims at converting structured data to human-readable text. For example, here we have a knowledge tribal about a person. Then we hope we can generate a natural sentence describing it. However, currently this task is still quite limited to a few particular domains. This is because the generation model should be trained on a well-aligned dataset, and this kind of dataset is difficult and expensive to get. As a result, existing datasets are either too small or only contains quite a few domains. So a natural idea is, can we train the model without aligned data? If this could be possible, we can easily extend this task to any new domains without well-aligned dataset. We aim to tackle the problem of completely unsupervised KB2 text generation, which only requires a text corpus and a KB corpus and does not assume any alignment between them. Unsupervised KB2 text generation is very challenging. It suffers from the following four problems, and we propose novel components to solve each of them. First, it suffers from unaligned data problem. It means that it only requires a text corpus and a KB corpus and does not assume any alignment between them. We propose a dual learning framework to solve it. Second, it suffers from the non-differentiability issue. It picks words from our neural model before reconstruction. Therefore, it's hard to train the extractor or generator effectively using back propagation. To solve this issue, we apply reinforcement learning based on policy gradients. Third, it suffers from the cold start problem. Existing dual learning methods pre-train the model with labeled data and then fine-tune the model. They still need annotated data. Since we do not assume any aligned data, we propose a novel pseudo data generator to make pseudo data. Finally, it also has a multiple triple problem. The traditional RL method gives all triples the same reward scores, and we propose the allocated reinforcement learning to give each triple an independent reward score. Let's first look at the unaligned data problem. Traditional generation models are all built based on the sequence-to-sequence framework. They all require to be trained on well-aligned data. Since we do not have aligned data, we propose to use the dual learning framework. As shown in the figure, it contains two dual tasks. The first one is the KB2 text generation task. It converts KB triples into text. The other task is the triple extraction task. It extracts KB triples from plain text. The framework has two dual processes called KB2KB and text-to-text as shown in the figure. The KB2KB process uses the generator and extractor to convert KB into text and then convert it back. The text-to-text process converts text into KB and then convert it back. In both KB2KB and the text-to-text process, the score of the recovered output is non-differentiable. We propose to use the policy gradient to make it possible to update our model's parameters. Existing dual learning methods pre-train the model with labeled data and then fine-tune their models via unlabeled data. Such a mechanism still needs annotated data, and the data is difficult and expensive to obtain in the KB2 text task. To cope with the cold start problem, we propose a pseudo data generator, which can generate pseudo text and pseudo KB triples based on the given unaligned KB triples and the text respectively with prior knowledge. Multiple triples might be extracted from a text example, and inevitably, the neural extractor could extract some wrong triples. The traditional dual learning approach, if directly applied, will regard all these triples as one unit and calculate a single reward for all the triples regardless of whether they are correct or not. It not only results in the slow convergence of RL, but also leads to unsatisfactory model performance. As shown in the figure, the left part is the traditional RL method, and the right is our proposed ARL method. 4 triples are extracted by the extractor. The top 2 triples are right and the others are wrong. Traditional RL methods give a single reward, 0.9 for all the 4 triples, while our proposed ARL gives each triple a different reward. Then, the right triples and the wrong triples will be distinguished and optimized differently. Let's have a look at our models. Our EGD framework solves the problem in a totally unsupervised way. It contains 3 processes. The first process is a pre-train process. Here, both the extractor E and the generator G are trained with the pseudo data generated by the pseudo generator. The second process is the KB2KB process. It generates description text based on the given KB triples with the generator and then recovers the KB triples from the generated text with the extractor. The third process is called text-to-text. It extracts KB triples from the given text with the extractor and then recovers the text from the generated KB triples with the generator. To solve the cold start problem, we propose a pseudo data generator. In order to overcome the multiple mapping problem, we propose a novel allocated reinforcement learning component in KB2KB and text-to-text, respectively. Let's first have a look at the 3 processes. In the pre-train process, we first pre-train the extractor and the generator with the data generated by the pseudo data generator. For the text corpus TT, we generate corresponding pseudo KB triples as the first equation. Then, we pre-train the generator G to transform K to T. Similarly, we generate pseudo text as the last equation. Then we train the extractor to transform T to K after G and E have been pre-trained. The KB2KB process and the text-to-text process are conducted alternately to further improve the performance. In the KB2KB process, we first flatten the input KB triples and concatenate them one by one as K. K is then sent into the generator G to get a text description Tm. Afterwards, the extractor takes the sentences Tm as input and outputs the triple sequence K'. The loss function for the extractor is defined as the negative log likelihood of each word in K. We also propose the ARL component improves the generator. We will introduce this later. It is similar in the text-to-text process. The input text T is transformed into its KB representation Km by the extractor E. Km is then transformed to T' by the generator and the loss is defined with the negative log likelihood. We also propose the ARLE to optimize the extractor. Pseudo text generator generates pseudo text for each KB and text. The extractor and the generator will be trained with the pseudo supervised training data. This method solves the cold start problem. For the pseudo text generator, we calculate the empirical distribution for each word PW for a list of KB triple. We sample head and tail entities as KS. The final sequence is generated by sampling from both KS and PW. This process can be expressed mathematically as the last equation. This pseudo text data is used to solve the cold start problem when training the extractor. Pseudo KB generator generates pseudo KB triples for each text and form a pseudo supervised training data. This data is used to solve the cold start problem when pre-training the generator. For an input sequence T, we randomly remove words in the input text with a probability beta 1 and sample new words by sampling words from a distribution with a probability beta 2. The generated sequence k tilde is the pseudo KB sequence for each text. It can be denoted with this equation. ARLE is shown in the right part of the figure. The main idea is to recover and evaluate the KB triples separately. It firstly sends the input text into the extractor E and gets the extracted triples Km. Afterwards, the generator is applied on each triple in Km to recover the corresponding text T'. We calculate the reward for each triple and the recall for each corresponding generated text. Our RL used a different reward for each generated triple. The gradient is denoted as the last equation. ARLG is applied in the KB to KB process. The input KB triples is firstly splitted as K. It is then sent into the generator separately and gets the corresponding description sentences Tm. Afterwards, the text is sent into the extractor to recover the input KB triple for each text. We calculate the reward for each text as the precision for the corresponding generated triple. The gradient is shown in the last equation. Similar to ARLE, we also train the model with the text-to-text process to give a targeted sequence to guide the training together with the reward score. Let's see the experimental results. We adopt the WebNLG v2 dataset. It samples KB triples from DBpedia and annotates corresponding text by crowdsourcing. We split the original dataset into KB part and the text part. We do not assume any alignment between them. This table shows the statistics of instances with different number of triples. We compare our model with some baseline methods. The first is the PDG model. It only uses the pseudo data generator to generate the pseudo data for pre-training both extractor and the generator. It does not conduct the subsequent dual learning process. The DL model uses the dual learning process. It fine-tuned on the PDG model and iterates alternately between text-to-text and KB-to-KB process. Here, we do not use any reinforcement learning component. The DL-RL1 model uses the dual learning process together with an RL component. It uses the log likelihood of the recover process output sequence as the reward. The DL-RL2 model uses the ROG-L score of the recovered sequence instead of using the log likelihood as the reward. The SIG model is a supervised extractor generator using the original setting of the WebNLG for both generator and extractor. It provides an upper bound for our experiments. Both generator and extractor of our model outperform all baseline models significantly and consistently. The comparison between our EGD model and the supervised SIG model indicates that our unsupervised EGD model is close to the bound of the supervised methods. Our proposed pseudo data generator and allocated reinforcement learning help improve the performance. In this experiment, we conduct an error analysis for the top 20 mentioned relations. We focus on two kinds of errors. The first is false negative. It means when extracting some correct triples are ignored. The second is called false positive. It means that the extractor generates some incorrect triples that the text does not mention. It can be observed that the false negative problem is much more severe than the false positive problem for the PDG model, and our proposed EGD model alleviates this problem a lot. This table shows a case study for 4 models. The input for the extractor and the generator are given as this. It shows in the table our EGD model solves the false positive problem by the RL component. The result of the generator shows that it is more difficult to generate a sequence than extracting triples. Here are some conclusions. We propose a new challenging task called unsupervised KB2-text generation. To solve this task, we propose an extractor generator dual framework. It contains KB2 text generation task and the triple extraction task. To handle the cold start problem and the multiple triple problem respectively, we propose a novel pseudo data generator and an allocated reinforcement learning component. Experimental results show that our proposed method successfully resolves the observed problems and outperforms all the baseline models. Thank you.